time for us to do some problems involving properties of the gradient, which is a wonderful tool that we have to help us understand how things are changing, find tangent planes. Also, we get to talk about linearization. Fun stuff, wonderful stuff. And as we do it, it's important to pay attention and practice. Practice is how we get better, how we turn into our calculus champions. So make sure you do as much as you can. And if you're following along with the video, make use of the pause button. See a problem that you like? Pause it and try it yourself first. The more that you do, the stronger you'll get. Well, let's begin. Our very first problem. Find an equation of the tangent plane to the surface x squared plus xy plus y squared plus z squared equals 16 at the point 1, 2, 3. Now we could, if we wanted to, we could solve for z in this case. We maybe can't in some cases, but here we could. But it's actually beautifully set up for us. Because what do we have? Well, we have on this side a function, f of x, y, z. We say, okay, so we really have what? F of x, y, z equals 16. Now we're after a tangent plane. Whenever you hear a problem that says find a plane, you should think to yourself, ooh, I need to have a point and a normal. Well, we have a point, so what's our point? Well, it's 1, 2, 3. Great, easy. What's our normal? Well, the nice thing is that when we have our expression, a function f of x, y, z equals a number, then the normal is actually very easy to get. You do the gradient of f evaluated at the point 1, 2, 3. The idea here is that the gradient is perpendicular, which means normal, to the surface. And we can think of this as a level surface of some higher dimensional function. Ah, okay, all right, good. Well, so this is not so bad. We kind of have a plan. We're going to take our gradient, plug in our point to get our normal vector, and then once we have our point and normal, we'll get our plane, and life is good. So what's our gradient? The gradient of our function, well, that is, recall, the set of partial derivatives. So f sub x, f sub y, f sub z. So taking the derivative with respect to x, okay, so we get 2x and a y, and that's it. So 2x plus y. Take the derivative with respect to y. There will be an x and a 2y. All right, great. Take the derivative with respect to z, and we're going to get 2z. Now you might be wondering, 2z or not 2z? That is the question. No, it's 2z. All right, great. Well, that's our gradient. Now remember, we don't have our normal vector because we want a vector with numbers, not with a function. This is a function. The gradient vector is a vector-valued function. And so we want to get down to just a set of numbers, so we need to evaluate. So plug in 1, 2, 3. Well, that means everywhere where we see an x, we put a 1. Where we see a y, we put a 2. Where we see a z, we put a 3. So we're going to have 2 times 1 plus 2. That makes it 4. Then we're going to get 1 plus 2 times 2. So 1 plus 4 makes it 5. 2 times 3, 6. Okay, so our point is 1, 2, 3. Our normal is 4, 5, 6. All right, well, we have our point, we have our normal. We're basically home free. So our plane is 4x plus 5y plus 6z equals something, right? Because that's how we get a plane. Once we have a normal vector, the normal vector are the coefficients. We just need to figure out what the something is. And for that, we use our point. So we take our point 1, 2, 3 and plug it in. So 4 times 1, 4, 5 times 2, 10, 6 times 3, 18. So 4 plus 10 plus 18 gets us up to 32. So 4x plus 5y plus 6z equals, not 30z, Steve, come on. 32, there we go. Well, other than a small slip, that's it. That's not so bad. Great, wonderful. And indeed, finding tangent planes to surfaces like this are now pretty straightforward. It's almost easier to find tangent planes in this way. The only thing you have to remember, we didn't have to worry about it this time, is that you have to have something equals a number. So if it's not a number on this side, then just move everything across so that it is a number. All right, good. Well, nice warm-up problem. Let's keep going. So our next problem. Suppose, here we go, f of xy is 5x plus 3y minus x squared y plus 2xy. In which direction, given as a unit vector, in the inputs, should one initially move from the point 1, 2 to have the largest rate of decrease? Okay, so what are we looking for? We want to make sure we know what our answer is going to look like. We know we're looking for a direction, which is as a unit vector. Okay, so in other words, our answer should be a vector. And that answer corresponds to a direction. Now, what's the key? What's the key phrase here? The thing that makes us say, oh. Well, the key phrase is this part right here. Largest rate of decrease. That's the part that makes us say, wait a second. There's something really cool going on. You see, our gradient has some very nice interpretations. And one of the things that we can do is that we can interpret the gradient as giving us information about how we move to maximize our increase, or if we want to do the worst thing, go down as largest rate of decrease, that means go in the opposite direction. So recall, gradient of f at 1, 2, this points in direction of greatest increase, or if you like, whoops, we can spell the word direction, of largest increase. And so that's a nice property. So minus the gradient is very similar. It points in the direction of largest decrease. So if you go against the gradient, you're going to be going down as fast as possible. Okay, so now we kind of have a plan. Because we know we're looking for the direction of largest rate of decrease. So it says, hey, figure out the gradient, take the negation so that you point in that direction. That's the right direction. Now, it's not our answer, but it's the right direction. So let's get to that point, and then we'll talk about how we can finish up to get our answer. So we start. The gradient of f is, okay, partial derivative. Take derivative with respect to x. 5. And let's see. Oh, no, I'm not done yet. I put a comma too soon because there was more x's. 5 minus 2xy plus 2y. Okay, now a comma. All right. Now, derivative with respect to y. 3. There's a y there, so minus x squared. And there's a y there, plus 2x. All right, so there's our gradient vector, gradient function, whichever way you like to put it. We're going to evaluate it at the point 1, 2. So everywhere where we see an x, we put in a 1. Where we see a y, we put a 2. So we'd have 5. 2 times 1 times 2, 4. 2 times 2, 4, comma. Here, let's see, we get 3. Then we have minus 1 and plus 2. Okay. Great. There we go. Well, we clean it up. 5 minus 4 plus 4. Well, what'll that be? It'll be 5. Okay, good. And, What else? Well, 3 minus 1 plus 2. 4. Okay, so we're almost there. So the negative of the gradient would be -5, -4. Now, this is good. Right direction. What's wrong? Well, the problem is, what's our answer? You see, it was very clear. Direction given as a unit vector. Okay, the problem is, it's not a unit vector. Wrong length. Okay, well, that's easy. We have ways to deal with that. What are our ways to deal with that? Well, what we do is we say the following. Say, okay, let's take our vector, divide by its magnitude. So we're going to do 1 over the magnitude of -5, -4 times -5, -4. Well, that's 1 over square root -5 squared, 25, -4 squared, 16, times -5, -4. Okay, which gives us 1 over the square root of 25 plus 16, not the greatest number. I mean, not a terrible number, but it's not a perfect square. It's 41. Well, that's okay. So 1 over the square root of 41 times -5, -4. And that's it. That's the direction we want. So if we head in that particular direction, and it's the unit vector, that will get us going downhill as fast as we possibly can. Which, maybe we want to go downhill as fast as we possibly can. Maybe we want to go, for example, to a minimum. Well, good. Go that way. You'll get there pretty quick. All right. Well, good. Good problem. Well, let's move on and do another one. So, our next problem. Suppose that our function, f of x, y, z, is a differentiable function. Well, that just means we can take derivatives and do things like gradients, for example. And at the point 1, 3, 2, the maximum rate of change of f is 14 and is achieved in the direction starting from the point 1, 3, 2 and going towards the point 3, 3, 5. Okay, all right. There's a lot of information to parse in that sentence. We'll come back to it. Find the rate of change of f in the direction from the point 1, 3, 2 and going toward the point 3, 5, 1. All right. Well, let's see if we can figure this out. Okay. First off, we see they're throwing around this phrase, rate of change. They actually use it a couple of times. Find the rate of change. We're told about the maximum rate of change. Now, when you see words like rate of change, we say, oh, they're just trying to have a fancy way of saying derivative. So, all right, so we know something about the derivative here. And we say, okay, it's a derivative, and we see the words direction. Okay, great. So there's directional derivatives coming into play. Because our function is differentiable, the way you do a directional derivative with a differentiable function is we're going to use gradients. So we say, perfect. All right, so this is a gradient problem involved in some sense. Of course, how? We're still working on that. We'll figure that out as we go along here. Okay, so let's come back to our first sentence. Now, there's another key word here. And notice it's right here. The maximum rate of change. We already have the clue, because it's directional derivative, that this has something to do with gradient. This is reinforcing that clue. You see, when we talk about the maximum rate of change, that's built into the gradient. We say, okay, so what we know is the maximum rate of change turns out to be the magnitude of the gradient. So the fact that the maximum rate of change of f at 1, 3, 2 Well, that's found by taking the magnitude of the gradient of f at 1, 3, 2. And so we can rewrite that. Okay, so again, when you're looking for maximum rate of change at a point, it's the magnitude of the gradient at that point. And then the is 14 is equals 14. So we know the magnitude of the gradient. Now, the nice thing is the gradient is a vector, right? And vectors have two things. They've got magnitude and they've got direction. So if we could figure out the direction, we'd actually have the vector. And notice that there's a word and. Oh, cool. And is achieved in the direction. It's in our direction. Okay, starting from the point 1, 3, 2 and going towards the point 3, negative 3, 5. Okay, so let's actually dig into that. So we have this point here, this point 1, 3, 2, and it's going to this point 3. Let's say it's over here. I don't know. We're just making things up at this point. We're working on our intuition. We don't need to be precise. We're just trying to get the picture. We know that this direction here, between those two, that's the direction of the gradient, because that's saying this is the way to go to maximize your rate of change. So let's see, what do we have? Well, look at the differences. 3, take away 1. Says you went up by 2. Negative 3, take away 3, went down by 6. And 5, take away 2, says you went up by 3. So 2 minus 6, 3 is in the same direction as the gradient vector. Now, is this the gradient vector? And why not? Well, you're right, it's not. Okay, good. But why not? Let's just be clear about that. Well, the problem is it may not be the right length. So we've got to make sure it is the right length. Okay, so now to do some work on the length. All right, so in essence, this vector is close to the gradient. It just needs to be scaled properly. Okay, so let's figure out how we need to scale. So if we take the current length, 2, negative 6, 3, and figure that out, that'll give us our clue. All right, so that would be the square root of 2 squared, 4, negative 6 squared is 36, because the square of the negative goes away. 3 squared, and 7 years ago, wait, no, that's not it. 3 squared is 9. 4 plus 36 is 40, plus 9 makes 49. That's a nice number. Square root of 49 is 7. Now, this vector has the right direction, but has length 7. I want a vector with this direction, but length 14. So what can I do to a vector that has the right direction, length 7, to get the right direction, but length 14? Well, I scale. But what do we scale by? We scale by 2, right? To get from 7 to 14 multiplied by 2. So, putting this information together, the direction information, the magnitude information, we come to the conclusion that the gradient of f at the point 1, 3, 2 is equal to, doubling here, 4 minus 12, 6. All right, fantastic. We now have our gradient. So we've taken the first sentence and pulled out the gradient, which is great because we need that for the second part, right? Find the rate of change from this point 1, 3, 2 towards the point 3, 5, 1. So what goes on here? Well, now you have some point, let's say over here, 3, 5, 1. And we're trying to say, what's that? All right, this is almost surely not in the right place in the picture. But again, the picture is just for intuition. Okay, so, well, let's start by figuring out what is that vector that's pointing there. So 1 to 3 says we went up by positive 2. 3 to 5 went up by positive 2. 2 to 1 says we went down by 1. All right, so it's 2, 2, minus 1. We want to head in that direction. Now, that's not quite the vector we need, though, because it's the right direction, wrong length. We need a unit vector. Okay, we have ways to fix that. So what we can do is divide by that magnitude of that vector. Well, this one, might be able to do this in our head. Squaring 4, 4, and 1 makes 9. Square 9 is 3. So this becomes 1/3, 2, 2, negative 1. So that is our unit vector. This is our u. Now we put it all together and we'll get our answer. So we get the following. We're going to take our gradient of f at the point 1, 3, 2, dot it with u, which is our 4 minus 12, 6, dot it with 1/3, 2, 2 minus 1. All right, so I can pull out the 1/3. Dot product, 4 times 2, 8. Minus 12 times 2, ooh, that's a big number, minus 24. 6 times minus 1, minus 6. Okay, all right, so what do we get? Well, we get 8 minus 30, which would be negative 22, and then, of course, over 3. And we're done. That's it. Negative 22/3. So that is the rate of change that we were looking for. So this is kind of a fun problem because it doesn't feel like we have a lot of information, but we were like, oh, we're being given information about the gradient in terms of its magnitude and in terms of its direction, which allows us to reconstruct the gradient. And once we have the gradient and we have our direction, we can find our rate of change that we're after. Ah, wonderful. We succeeded. Kapla! Which, of course, we all know is Klingon for success. All right, good. Well, let's continue. On to our next problem. Okay. Given that f of s comma t is 2e to the power s minus 3t plus s squared minus 4t, use the linear approximation of f of st at the point 3, 1 to estimate f of 3.1, 1.1. Now, it sounds complicated because they use this very big word, linear approximation. But even though it's a large word, we really say, tangent plane. That's what it is. Linear approximation means tangent plane. Well, so what do we need? If we have the tangent plane, we just use it. Because the idea here is that our function, well, this is what really is going on here. Our function is approximately the tangent plane. Now, what do we mean by approximately? Well, it's not exactly the same because our function tends to be a little bit more wavy, right? And planes are flat. But the approximation is good near the point of tangency. And that's what's happening here. You can see, it says, look, you find the linear approximation at 3, 1, which means I'm looking for the tangent plane at 3, 1. And this point, 3.1, 1.1, is pretty close to 3, 1. So, all right, we have kind of a plan. What do we need? Well, we need to find our tangent plane. So I should pause and point this out again. Look, we might have these variable names s and t. It's really no different from x and y. It doesn't. Same principles, same philosophy at work here. So we say, all right, great. So if what we did for x and y, do the same process, right? Okay, so what would we do? Well, we'd have our function at a, b, plus the partial derivative with respect to the first slot, which was now f sub s at ab times s minus a, plus derivative with respect to the second slot, which we'll call f sub t at ab times t minus b. That's our tangent plane, our linear approximation. So we can say, hey, f of st is approximately this. Keeping in mind, of course, the approximation is only good when we're nearby. All right, well, we need to fill in some slots here. Let's do some work here on the side. All right, so writing down our function again, f of st, that's 2 e to the s minus 3t plus s squared minus 4t. F sub s, well, take care with respect to s. There's an s up here, so that'll be 2 e to the s minus 3t times the derivative with respect to s of the inside, which is 1. That's good. Derivative of s squared is 2s. Take the derivative with respect to t. So, of the original function, all right, well, there's a t there. Now notice when we take the derivative of the inside, there's a negative 3 that comes down. So it's really negative 6 e to the s minus 3t. And then s squared goes away because we're taking it with respect to t, and minus 4. All right, now those are our partial derivatives, but we need to evaluate. And so we plug in 3, 1, because that's where our tangent plane is being formed. All right, well, f of 3, 1. So we're going to have 3 minus 3. So that's e to the 0. E to the 0, also known as 1. Great. So we're going to have 2, 3 squared, because s is 3. So that would be 9. 4 times 1, that's minus 4. 2 plus 9 minus 4, 7. All right, good. F sub s at 3, 1. Again, it's going to be e to the 0 times 2, which is 2. Then 2 times 3, because s is 3. So 2 times 3 makes 6, which gives us 8. Okay, and then f sub t at 3, 1. Okay, again, e to the 0, 3 minus 3, times negative 6, makes that minus 6, and then minus 4 more. So when we put this all together, well, we're going to have a 7 in the slot there, then an 8, and then we're going to have a, whoop, forgot to write down, negative 10. Whoa, that's very negative there. Okay, and then don't forget, well, s minus 3, because we're at the point, the a corresponds to 3, and t minus 1. Okay, so we get 7 plus 8 times s minus 3 minus 10 times t minus 1. Now, we're almost done. Aha, our function is approximately our tangent plane. We have our tangent plane. So the last thing to say is f of 3, 1 is approximately, see, it's all about approximation, which is good because we're after an approximation. Well, 7, not f of 3, 1, 3.1, 1.1. I am so sorry. F of 3.1, 1.1. Okay, but again, it's approximation. So that part was right. 7 plus 8 times 3.1 minus 3 minus 10 times 1.1 minus 1. Okay, so that's 7. 3.1 minus 3 is 0.1 times 8 will be 0.8. 1.1 minus 1 is 0.1. I take 0.1 multiplied by minus 10, that'll be minus 1. So we have 7 plus 0.8 minus 1, which gets us to a grand total of 6.8. And there we go. That's it. That's our approximation. Is that a good approximation or a bad approximation? It's a reasonable approximation. So in other words, using the information that we'd have, it's the best approximation we could expect. All right, well, good. Let's continue. On to our next problem. So, here we go. Part A, two-part problem. Find the tangent plane to the surface x squared plus 3xz plus sine of 2x plus y minus log of xz equals 4 at the point minus 1, 2, minus 1. Okay, haha. Well, that looks terrible, right? But actually, it doesn't, because it's in the kind of the nice form. Now, you might be thinking, ooh, what's the nice form, Steve? Well, the nice form is, if you think about it, what you have is this crazy-looking right-hand side is really some function f of x, y, z. So we really have capital F of x, y, z equals 4. And now we say, well, that's the ideal situation to be in. Because if I have that form, I can find the normal vector very easily. See, I already have the point. Now, how do we have the point? Well, because they gave it to us. So we can say, look, our point is going to be minus 1, 2, minus 1. So we need the normal. And once we have that, we've got our plane, and life is good. So to get the normal, we say, okay, that's going to be the gradient of f at minus 1, 2, minus 1. Because that's how we can find it. We see what's going on is we have this nice surface that's really like a level surface. And the gradient is perpendicular to our level surface. So we start by taking our gradient. So the gradient of f is, take the derivative with respect to x. Well, 2x plus 3z. Here we do the chain rule. It'll be cosine of 2x plus y. And we multiply it by the root of the inside, 2 will come out. So it'll be 2 cosine 2x plus y. And here, derivative of log of xz, well, what is that? It's going to be a minus. You can write it as, put it the inside. Okay, that's x times z, times by the root of the inside, which is z. Comma. That's just the first entry. There's 2 entries to go. All right, the next entry, derivative with respect to y. There's no y, there's no y. Aha, there's a y. Okay, well, what is that? Cosine of 2x plus y times 1. And no y there. Oh, that's a nice entry. Good. Now the z. No z, there's a z. Okay, that'll be 3x. No z there. And, okay, similar thing. Okay, minus xz on the bottom, derivative of xz with respect to z, puts an x on the top, and we're done. Okay, there we go. That's our gradient. Now, plug it in. Plug in our point. Gradient of f at minus 1, 2, minus 1. Okay, so everywhere where we see an x, put a negative 1. See y, put a 2. A z, put a negative 1. So actually, x and z both get negative 1. So that's kind of nice. So we're going to get minus 2 and a minus 3. So that's minus 5. Here, we're going to get 2 times cosine of 0, because it's minus 2 plus 2. Cosine of 0 is 1. So there's a plus 2. The last part, the z's cancel. So it's really a minus 1 over minus 1, which makes a plus 1. In the middle, getting a cosine of minus 1 plus 2 cosine of 0, 1. Last entry, minus 3, the x's cancel, then it's minus a minus 1, because 1 over minus 1 is minus 1. So it's really minus 3 plus 1. So we end up with minus 2, 1, minus 2. Okay, there we go. That's our gradient. Minus 2, 1, minus 2. Okay, well, kind of strange. It kind of looks vaguely like our point. Coincidence. Coincidence. Don't read too much into that. Now, we're not done, but we're close to being done. How do we finish? Well, now that we have our point and our normal, we can combine them together. And so, if we do that, we're going to end up with our tangent plane. So these are our coefficients, minus 2x plus y minus 2z equals, okay, now we plug it in our numbers. That'll be positive 2, positive 2, positive 2, so it equals 6. All right, good, success, success. Now, that is one way we can write our answer. There's another way we could write our answer, which, well, let's just leave it for here for now. Now there's this question. Part B. Okay, so we'll say we'll accept this for part A. Part B. Estimate the value of x that satisfies this relationship when y is 2.02 and z is negative 0.96. Now, you might think, okay, where to begin? Well, it's part B of a problem. And there's a nice philosophy. If you have a problem with multiple parts, part B is oftentimes related to part A. True story, true story. Okay, so part B, we think about what happened in part A. Well, part A was saying, find the tangent plane. And now we say, aha, wait a second. We know that the tangent plane that we just found is really an approximation to our surface. And so we're not thinking this as a function because we wouldn't be able to solve for z. So I'm not saying z is, some easy function. In theory it is, but we may not have it. But definitely there's a surface. So okay, so the tangent plane acts like the surface nearby. Okay, in particular, near the point minus 1 to minus 1. So what we can do is we can say, all right, let's use the tangent plane as a stand-in. So that's why it says by using the tangent plane from part A, because the tangent plane acts like our surface nearby. So what can we do? Well, we literally just do what it tells us to do. It says what? Plug in y and z, and we can solve for x. Because what we're really doing is we're saying, use what you know about y and z, and to figure out, if you know y and z for the plane, you know x for the plane, and that would be an approximation for the surface. All right, so if we do it here, we can say, minus 2x plus, all right, 2.02 minus 2 times minus 0.96 is going to be equal to 6. Okay, and solve for x. This looks not fun, but notice we can do some things. We can divide everything by 2, and we say, okay, minus x plus 1.01 minus makes plus 0.96 is equal to 3. All right, well, that's good news for us. Okay, and we can even say, look, 1.01 plus 0.96 is what? It's 1.97. Now, we're just going to do a little bit of rearranging. Move the minus x across, move the 3 across. We can say x is 1.97, subtract 3. All right, well now we're almost home free. That's going to be a negative number, and in particular, negative 1.03. So that value, negative 1.03, that's what's happening on the tangent plane, and the tangent plane is an approximation for what's happening on the surface, and therefore that is giving us a reasonable estimation. It's not perfect, and it's definitely not exact, but it's an approximation, an estimation. As a general rule of thumb, when we start seeing things like estimate or approximate, usually it's a signal that a tangent plane is being used in some way, shape, or form, because the tangent planes are approximations nearby. All right, good. Well, I think we have time for one more. One last problem. Your company is a leader in widget manufacturing. Woohoo! Nice, widgets. They're small cylinders. Now, widgets are supposed to have a radius of 2 inches and a height of 3 inches. So it's kind of a very stout cylinder. So, all right, so we have our widget. All right, so it's supposed to be 3 inches in height and 2 inches in radius. Okay, but no widget machine is perfect, and there are always small defects. In fact, this is a true thing. When you're dealing with a manufacturing process, you can say, look, this is what we want, but they're going to say, okay, I know you want exactly this, but the machines aren't perfect. There's always going to be a small amount of error, and so we want to make sure we account for that. And so there's going to be some kind of a defect. And we have to say, well, how much can we tolerate? That's our question. Well, here we go. Given that the volume must be within pi cubic inches, so that's our total tolerance. It says, look, I understand that it's not going to be perfect, but I have to be within this amount of volume. And it's already known that the height is within 0.1 inches of being correct. How much can we allow the radius to vary? And it's an estimate. And now we're like, ooh, this is a good word for us, estimate. So when we see estimate, kind of in the back of our heads thinking, okay, kind of a tangent planey thing going on. So let's dig into it and think about what's happening here. One of the ways we can think about our tangent plane is the following. All right, so in our case, let's actually write down our basic formula. So the volume of a cylinder, it's not so bad, it's pi r squared h. And so if we think about our tangent plane using our symbols here for variables, we can say, well, look, there's the volume, radius, and the height. And what we can say is the following. Our change in volume is approximately the derivative of volume with respect to radius times the change in radius plus the derivative of volume with respect to h times change in h. Now, what's happening? This may not feel like tangent plane, but it really is tangent plane. You see, the tangent plane, we usually think of this as like x minus a and y minus b. Well, that's what the delta r and delta h are, and they're just using different symbols. So it's rate of change in one variable times the amount of change in that variable, or rate of change in the other variable times the amount of change in that variable, and then we combine them together. And that gives us an estimate for the rate of change of the total. Okay, so let's keep digging into this. So for our case, we would say what? Well, change in volume is approximately, well, if we take the derivative with respect to r, that'll be 2 pi rh times the change in r. Take the derivative with respect to h, pi r squared times change in h. In some sense, this is kind of like the chain rule here, but now we're going to evaluate. Okay, so we care about the following situation. We want R equals 2, H equals 3. So our change in volume, which is how much our widget is off by approximately, is, and we'll plug this in, 2 times pi times 2 times 3. Well, that's 12 pi times however far we were off in our radius, and then pi times 4, 2 squared, 4 pi times our change in our height. So that's roughly where we're off. And now we start to be like, okay, here we go. What can we say? Well, our volume, now our tolerance, we say, look, we want to be within pi. So that's how much we want pi to be. We also know our height, well, that's within 0.1. Now notice I'm putting here plus or minus, which says I can vary either way. I could be a little bit too tall, I could be a little bit too short. So that's why we put plus or minus. And then there's this change in R, which is what we're trying to understand. All right, well, let's clean this up a little bit. Everything has a pi in it. So if we divide through by pi, we could say, look, our tolerance, we need to be within 1, and that's going to be approximately 12 times however much we can afford to be able to give away in terms of the radius, plus 4 times 0.01, so within, whoops, okay, there we go, within 0.4, there we go, that was a 0.4. Okay, so now the question, what can we say about that little piece left? Well, and I know this is kind of feeling weird because it's like, I have all these squiggly lines and it's like plus or minus and things could be all over the place. But think about it this way. I at most have 1 to give. And just from the variance in the height, I'm already giving up 0.4, potentially up to that amount. So if I have at most 1, and I'm already potentially have lost 0.4, how much is left for me that I can sacrifice and still not go over? And the answer is this part right here. I have to make this within 0.6, right? Just think of it as the full thing is 1. I already have 0.4 lost. There's 0.6 left that I have in terms of the wiggle room that I can play with. So 12 times the change in the radius has to be within 0.6. Finally, if we divide, we can say, all right, so our change in our radius has to be within plus or minus. That's our tolerance. We can go up or down because you can imagine, well, both things are too big. Okay, both things are too small. Now, of course, if one goes up and one goes down, they might cancel out a little bit, but, you know, we don't know. We're thinking of them as being independent. All right, 6 divided by 12. Well, actually, it's not so bad, right? Because you can think of 12 as 6 times 2. So you can think of the 6's as canceling, and 0.1 divided by 2 would be 0.05. So that means we need to be within 0.05 inches, or a 20th of an inch. So we've got to be really careful with our radius. So our radius can't vary by more than 0.05. But as long as we keep it within that amount, our widgets will be good to go. Wonderful. All right, well, good problem to finish on, right? And keep working and keep doing more problems. You're going to become great. I believe in you. Hope you have a great day.